Hi, and welcome to the third and last module on classification. Last time, we have seen in details how a multilayer perceptron works and can be used for classification. In this lecture, I'll give you an overview of a few other different models, such as support vector machines, k-nearest neighbors, decision trees, and Bayesian networks. Then we will see also the advantages of combining classifiers, and I'll give you some references to packages in different languages and online tools that you can use to solve your pattern recognition problems. Now, let's start with the k-nearest neighbor. It's a very simple model, and it's often used as a benchmark. It is a crispy classifier, and the output is the class membership. Each new object is assigned to the class most common among its k neighbors. It is a so-called lazy learner since the function is only approximated locally and all the computation is deferred at classification time. Now, the choice of k is crucial and depends on the dataset. For example, large k reduce the effects of noise, but make boundaries between classes less distinct. And in this model, the accuracy also degrades in presence of irrelevant features, so a good pre-processing is needed before applying it. Now, let's see briefly how it works. Suppose we have two classes, like in the figure, blue squares and red triangles, and we have a new data coming in, and we want to classify it. This new data in the figure is represented as a green circle. Now, if k is equal to 3, it is assigned to class 2 because, as you can see, there are two triangles and one square in the inner circle. Basically, the first three neighbors are two triangles and one square, and that's why it's assigned to the triangle classes. If k is equal to 5, it is instead assigned to class 1, and that's why the choice of k is really crucial in this class of models. Now, another model very useful, especially when dealing with missing data, is the Bayesian network. And Bayesian network can be represented through a directed acyclic graph where the nodes represent variables and the missing arcs represent conditional independent assumptions. One of the main advantages of this model is, as I said, is robust respect to missing data, and the outputs are probabilistic. Now, briefly, we need to choose the topology. We need to generate priors and probabilities for each class. We then run each new event through the network in order to classify it. And then we can feed the new data back in to refine the priors, once we have verified that they are actually belonging to that class. Decision trees are a non-parametric models, and they are among the most used supervised classification algorithms. Briefly, a decision tree can be seen as a set of simple rules. For example, if the feature 1 is less than x and feature 2 is greater than y, classify this specimen as a AGN. So, in a decision tree, the internal nodes denotes test on the attributes, and the leaves represent the class label. Decision trees will be covered in much more details in Thomas' lectures. Now, support vector machine is another model that can be applied to both classification and regression. For any particular set of two class objects, they find the unique hyperplane having the maximum margin. Now, let's see what this means with an example. Suppose we have two classes like in the figure. In this example, the hyperplane in green doesn't separate the two classes at all. The one in blue does it, but with a small margin than the one in red. that it's the optimal choice in this case, since it has the maximum margin. SVM can also be used as a nonlinear classifier. So training vectors are mapped in a higher dimensional space using nonlinear functions. This space is called the feature space, and it is a high-dimensional space in which the class can be linearly separated. Now, the mapping in the higher dimensional space is done using the so-called kernel functions. Most commons are shown in the slide and are linear, polynomial, RBF, and sigmoids. For example, suppose we have two classes, like in the picture, crosses and dots, and we want to separate them. We can easily see that the linear kernel doesn't work well. It's the first one. While the polynomial kernels work better, but still we need to be very careful with the overfitting that it's likely happening in the last case, where we are just connecting the dots. So this model will not be able to generalize well. Okay. So far we have talked about single models, but we can also combine them. In fact, it is often found that improved performances can be obtained combining models together in some way instead of using a single model in isolation. The advantage is that individual classifiers may be optimized or trained differently. So some classifiers could work better than others in recognizing some classes or in presence of certain input parameters. Some can deal with missing data while some others not, and so on. One example is given by a committee of machines, where we, like the one on the left, where we can have a combination of experts that vote together of a given example. Basically, each input object is given an input to each of the classifier, and then can be classified according to the class that gets more votes. Another way to combine classifiers is having a two-level network, where the output of the first networks, plus some additional information, are given an input to the second network. These are other two ways of combining classifiers, where the choice of which classifier to use is driven by an external parameter, like the seeing or the outside temperature. Now, suppose we have a bunch of neural networks, each one trained according to an external parameter sigma. In this example, if sigma is equal to 2.1, in the first network, just the first classifier will be activated, while in the second networks there are overlaps between the classifiers, and so the second and the third will be activated, and their outputs need to be combined in some way. Now, another way to combine different classifiers is using a sleeping expert framework. Sleeping experts can be seen as a generalization of the if-then rule. If the condition is satisfied, then activate the expert. So each classifier basically makes a prediction only when the instance to be classified falls within its area of expertise. In this example, we have 5 classifiers, an ensemble of KNN, ensemble of decision trees, Bayesian network, neural network, and a sort of supervised sum that can be activated according to the inputs, and also an external knowledge may be used to combine the results of the selected classifier to get the final classification. Now, let's see some of the packages that you can install or use online to do regression, classification, clustering, and other data mining tasks or data analysis. The first one is called Orange, and you can download and install on your machine for free. The website is on the slide and also on our webpage. It has many classification and clustering models, a pretty intuitive interface with widgets and drag and drop abilities, and can also be scripted in Python. So you can add functionality by yourself to this tool. And the newest version also supports data stored in a database. DAME is a web-based data mining tool specialized in massive datasets exploration. Doesn't have drag and drop abilities like Orange, but it is very powerful and can deal with the large datasets and can be used from the website. So basically you can just log in, build and run your experiments and get a notification when you are done. There are a few algorithms as well for regression, classification, and clustering, like k-means, self-organizing map, and many versions of multi-layer perceptrons. Weka is another tool widely used for data preprocessing, data mining, and data visualization. And in Weka, you can add your own Java code, so that become a new module. Like with Python in Orange, you can do the same using Java with Weka. Now, data mining toolboxes and libraries are pretty much available for basically any platform and any programming language. So like MATLAB, R, C, Java, Python, even for Lisp. So if you have your favorite programming language, you can find a list of useful resources on the class webpage, or you can just Google them or ask in the user groups. So, in this last module about classification, we have seen an overview of different supervised models that can be used for classification. Then we have briefly see how combining classifier can lead to better results, and also a list of useful resources that you can download or use directly online to solve your pattern recognition problems. The next series will be on clustering.